Alright, so here we are. We're going to talk about oceans and atmosphere as leading into weather, because obviously both of those have a big part of weather. We're going to spend a lot more time talking about the atmosphere, because we have atmosphere here. We're not as close to the ocean. We will talk about how it affects our weather, yes, somewhat, but we won't go into as much detail on tides and all that sort of thing. We're not going to do a lot of that for this unit. We're going to mostly focus on how it relates to weather, which is coming up next. Alright, now we talk about this planet, and we talk about the big blue marble or whatever, and for good reason. If you look at the Earth from space, one of the biggest characteristics you notice is blue, because large parts of it, if you look in the Pacific Ocean, like over here on this side, it's almost all water, hardly any continents. If you look on the other side of the hemispheres, you will see, of course, Asia and Europe and Africa. Over here you'd have North America over here and here, all right, and so forth. But there is a lot of our planet that is basically water, okay? And the source of all the water that forms in our weather, our rain, our snow, and all that comes from the water that evaporates from these oceans. So the number one thing, or probably biggest focus that the oceans have on weather, they are the reservoirs or the storage areas, okay, for the water that eventually will evaporate and becomes our rain. Now, oceans, of course, are salty, but the water, as it evaporates, forms clouds and eventually precipitation, and in doing that, only the water evaporates, leaving the salt behind. So technically, the oceans are getting saltier and saltier, and the water that evaporates out of them, though, is fresh once again. And so if it weren't for the evaporation of the water out of salt water, we would run out of fresh water. And so that's very important. Now, the second thing about this is water has what we call a high specific heat. Okay? And what high specific heat means, it takes a lot of heat to make the temperature actually increase. Okay? And so you can put a lot of heat to water, but its temperature doesn't actually go up very much. Now, if you're in an island country where you have a lot of water all around, okay, like this, or even on the west coast of the United States over here, or any of these other continents, okay, if you're near the ocean during the day, the land heats up, gets very, very hot very quickly, because it has what we call low specific heat. So a little bit of heat makes it heat up quickly, so it'll heat up during the day. All right, and at night it will cool down quickly. If you're out in the middle of a continent, sometimes we have various deserts scattered across the world. They're in the center, and because they're surrounded by land, they get very hot during the day, but they can get fairly cold at night, because land has a low specific heat, and what that means is it doesn't take much heat energy to make it get warmer, but it also loses it very quickly, and so if it loses a little bit, it gets colder fairly quickly. So deserts are characterized by high temperatures in the daytime, cold temperatures at night. On the other hand, if you live near the ocean heats up slowly. So, for example, along the west coast, the temperature in those cities next to the coast tend to be moderate. They don't heat up as much in the summertime. Okay, and then at night they don't cool off as much. The warm temperatures, as the water out here slowly cools down, helps keep them warmer. So their temperatures don't fluctuate from the day to night as much. They don't get as high during the day. They don't get as cold at night, so it keeps them more moderate. And also, this has to do during the winter. It keeps it warmer here, and in the summer it doesn't get as hot. And so when you're being near the coast, now you may have high humidity, and that we'll talk about in a minute. That's another problem, but that's a whole different deal. But in general, the temperatures are moderated by the fact that you have water nearby. And even the Great Lakes, for example, in North America and stuff, have that same similar effect as the oceans do. Alright, this is what's called a climatograph. Okay, climatograph just means it shows climate or weather data, okay, and how it relates. And we have two things here. We have San Francisco, which is kind of hard to read there, but San Francisco, and we have Kansas over here. And notice that in the summertime, it gets very hot in Kansas because it's surrounded by land on all parts, okay, whereas San Francisco is next to the ocean. And so San Francisco, even in July, August, September, is actually a little hotter there, okay. Their high temperatures don't get nearly as high as they do in Wichita Falls. In the wintertime, though, you'll notice Kansas gets extremely cold, okay? Whereas where San Francisco never gets quite, in fact, never has a average temperature below freezing point, okay? And that's kind of the basic thing here. Down here at the bottom, it points out the average temperature range in California is basically about 16 degrees Fahrenheit, and it's about 48.8 over here in Canada. So there's a lot more variation in the temperature, and that's primarily because San Francisco is next to the ocean, which moderates its temperature range. Wichita Falls is farther away. All right, now we'd like to talk a little more about the atmosphere, okay? What are the components, or what are the things that the atmosphere is made out of, okay? And notice, first of all, by far, most of our atmosphere, 78% of it, is made of nitrogen. Nitrogen is the primary constituent, okay? And nitrogen is something that does not really affect us one way or the other. Plants can't really use it. Now, nitrogen that's in the air, if it can be made in a form that's used by plants, is valuable for fertilizer. All fertilizers have nitrogen in it. And there are some lightning strikes will take nitrogen in the air and make it in a form that's available to plants. And when it's washed out by the rain, that's one reason why rain tends to make your garden grow better than just watering out of the faucet. All right, but it doesn't really affect us. We can't really use it a whole lot. All right, we depend mostly on oxygen, but only about 21% or 1/5 of the atmosphere is oxygen, and it's a good thing. If the whole atmosphere were oxygen, it would just blow up every time someone lit a match, because oxygen is highly flammable. So it's a good thing that's mixed mostly with nitrogen. All right, notice that adds up to about 99% of the whole atmosphere. So basically, we're breathing nitrogen, oxygen in when we breathe. Most of it's nitrogen, but but that's what we breathe. All the other gases that we think about are relatively small amounts of it. They are very, very small amounts, generally speaking. Okay, argon, neon, helium, okay, all very light neon gases. Methane, which would be farts, cows belching as they chew on their food, all kinds of different things breaking down and rotting. Hydrogen gas, very, very small percentage of it. Okay, carbon dioxide, which we breathe out and we depend upon greatly, and it is increasing. The amount of atmosphere is carbon dioxide in the atmosphere is increasing. Ozone, we hear a lot about the ozone that protects us, but look how small percentages it is. Carbon monoxide, which is poisonous, so that's a good thing. Sulfur dioxide, rotten eggs, and some of these others. Okay, other particles and pollen depends, of course, varying on the time of year and so forth. All right, but notice water vapor. Water vapor can go anywhere from 0 to 4%. So really, the biggest things that affect our weather are really the thing that affects it the most is that 4%, 0 to 4% of water vapor. Okay, so, and we'll talk more about water vapor later in our atmosphere, but just keep that in mind. The other thing we'd like to look at is the structure of the atmosphere, just a little bit, just to understand it. Okay, the first layer is the troposphere, which is down here. All right, our troposphere. All right, and troposphere, notice, is it goes up to about 4 to 8 miles tall, roughly. Okay, it's 8 to 16 kilometers, but that's less than about 8 miles high. But keep in mind, this is where all of our weather occurs. So weather is all in the troposphere. Okay, a little bit of it probably extends into the stratosphere, but just very little. You can see a few clouds up here. But for the most part, all of our weather happens in the troposphere. That's the part we live in. Okay, it is by mass, it is 90% of the atmosphere. So almost all the atoms, if you will, or matter, are crowded into here. Okay, it's very dense here because air has weight. We don't think about it having much weight because it's so small, but it has weight. And so basically the gravity of Earth pulls most of it down here into the troposphere. And so that's where most of the air, actual molecules. Up here, they're getting thinner and thinner and thinner. We talk about the air getting thinner. There's less and less particles as you get farther and farther away from the Earth, and that's because of gravity. Okay, and it just gets thinner and thinner until finally appears the exosphere, as we just start calling that outer space. But technically, they just get thinner and thinner until there's practically no air molecules anymore, and we say we're out in outer space. Okay. Now, generally speaking, in the troposphere, this is the temperature. This line here represents temperature, and notice it's decreasing. The higher up you go, higher altitude, it tends to get cooler. Okay, if you're up in the plane, once again, the temperatures drop. Okay, and eventually all the way to about negative 50 degrees Celsius. 0 is freezing, so it's 50 degrees below that. That's pretty chilly. Okay, so that's what's happening in the troposphere. All right, jets, for example, just to give you a thing, would fly at the top of the troposphere here, perhaps, especially if they need to get high enough to avoid bad weather and stuff like that. If they can't go around it, they might go above it, and so jets would just get up here into that just barely, and that's about as high as we regularly go if you're not on a space shuttle or something like that. Okay, above the troposphere, then we have the stratosphere. Okay, it goes from about 8 miles high to about 20 miles high, or 50 kilometers. Okay, so it goes up to about 50 kilometers, and the stratosphere is where we have ozone, O3. Okay, all ozone is just 3 oxygen atoms stuck together, whereas the oxygen we breathe is 2 oxygens stuck together. All right, ozone is very important up in the atmosphere because it helps absorb a lot of the radiation from the sun, and particularly harmful UV rays and stuff. We still have some UV that gets down to us here on the surface and can cause skin cancer or whatever, but there would be a great deal more if the ozone layer is destroyed, and so you hear a lot about people concerned about the ozone for good reason. Now, if it's on ground level, we have ozone, but that's actually considered pollution because it's not what we can breathe and it's not good. Now, basically, since it does absorb radiation, the ozone up here, notice the temperature goes back up to about 0 degrees Celsius. Okay, and so it gets up to about the freezing point of water up here at the top. All right, and that's pretty much the stratosphere. The stratosphere, the main thing, like I said, is the ozone layer. Now, above the stratosphere, we have the mesosphere. Meso just means middle for the most part. So, and this goes up to from about 25 to 20 to 25 up to about 40 miles or 80 kilometers high. Okay. Now, in the mesosphere, there's very thin air, getting less and less, and very little of it absorbs any radiation. So notice that temperature goes from 0 all the way down to negative 100. Some of the coldest parts of the atmosphere that we have. Okay, so it gets very, very cold because it does not absorb the radiation. Most of the radiation just passes right through it. Okay, now we get to the thermosphere. Thermo meaning heat, so you can guess it begins to heat up. The air particles up here begin to heat up extremely high. Okay, here's 100 where water would boil. These may be up to 200 or higher. Okay, almost up to 500 degrees perhaps. So they get extremely, extremely hot. But here's the deal. If you were to touch these air particles, here you're touching lots of air particles around you. Here the air particles are so far apart, yes, they have a lot of heat energy, but there's so few of them, it feels very cold. Okay, so the molecules are very hot. The air molecules up there are very hot, but there's very few of them. And so the net effect is, if you were to feel it on your skin, is that it is cold. All right. There's an important layer that's found here between the thermosphere and the mesosphere. Okay, and this is called it's not a separate layer, but it's a layer that has a lot of ions in it because it's called the ionosphere. Okay, because at this level, much of the sun's radiation comes and hits particles in here, and the radiation strips electrons from oxygen and nitrogen atoms. Okay, and if you rip off the electrons, as we learned earlier in the year, that gives them positive charges, and the electrons are stripped off or floating around in negative charges. So you have this strong area of many ions. Okay, and we will talk just a little bit more about those ions and why they're important on the next video.